Our exhibit is called The Quantum Revolution, and you might ask, well, what's all that about? Well, it's about applying quantum mechanics, quantum theory to information systems. So quantum mechanics is a theory that we use to describe the world on the very small scale, on the nanoscale in fact. So it describes the world of atoms and molecules. But recently it's also been very important for describing the components inside computers and communication systems, as they have shrunk to be ever smaller. Over the last 20 or 30 years or so, we've realized in fact that quantum theory can be used not only to describe the hardware inside a computer, but can also describe the software as well, or the information. So normally we think that information is something which is quite abstract and can be divorced from the hardware in which it runs. But in fact, information always requires some sort of physical representation. So that could be electrons inside a computer chip, or it could be photons inside an optical fiber, or ions inside a hard disk, but it always requires some sort of physical form. So in fact, information is just a state of a physical system, and we have to describe it with the same laws that we use to describe that physical system too. In other words, quantum theory. This has really been a revolution in the way that we understand information. But more than that, this quantum information technology, as we call it, also promises to provide a revolution in the type of information technology that we have. So for instance, we can use it to design new communication systems which allow us to directly test the secrecy of the communication, or to design computers which have really awesome computing strength. So in our exhibit we're going to show some of this new quantum technology and talk about how it can be applied to information technology in the future.
When you were last shopping online, did you rely on that padlock in your browser to protect your credit card details? How sure are you that it was safe? The scary thing is, somebody somewhere could have listened in and stolen your credit card details without you knowing anything about it. What we have here is an alternative technology which can tell if someone is listening in. This technology is completely different from that used by the padlock in your browser. Instead, it relies on the principles of quantum mechanics to guarantee the security. Information is encoded in single photons and sent along optical fiber. In this way, somebody trying to listen in will disturb the photons, thereby alerting the user. In the future, systems of this kind can be used to keep you safe online, as well as secure global networks and infrastructure.
Quantum teleportation is when quantum information is destroyed so it can appear elsewhere. It was named by its inventors who drew similarities between their invention and teleportation in science fiction. Quantum teleportation can't be used to move people between spaceships and planets, but it has some useful applications, for example in quantum computing. To teleport quantum information, we need pairs of entangled qubits shared between a sender and a receiver. One of these qubits is destroyed together with an input qubit, which has the action of teleporting the input qubit to the remaining receiver's qubit. Our researchers focused on optical quantum teleportation using photons. To begin, we needed a source of entangled photon pairs. Entangled photons have interconnected properties, such that measurement of one affects the other, even if it's far away. This is an effect which Einstein called spooky action at a distance. Our entangled light source is based on an LED, like you would find as blinking lights on your laptop. This was a big step because until then, all entangled light sources needed laser beams to drive them instead of electricity. Once we had our entangled light source, we used it to teleport quantum data here in this lab using optical fibers.